Alright, so it's been a couple of days. Yeah, the plan for today is to learn about Transformers, which I found this doc, which, I don't know, I might not use it, but it seemed to be okay quality from, like, skim reading it. I did make some progress off stream. Hold on, let me just full screen this. Yeah, so we did learn flags, and I did sort of stream. Maybe I should have streamed it, but I don't know. I was not really feeling it. So yeah, this is very basic. I just learned how to do XOR, and then also MNIST with CNN that like actually works. I need to actually take a look at some point, and this will probably be off stream because it's not particularly interesting. But my original MNIST network, and see why it wasn't learning. Yeah, the thing is, there's so many potential things that could be wrong with it. Flex makes it a lot easier, but then it also feels like you're kind of just like not doing any real work because, you know, the library kind of does all the hard stuff for you. Yeah. So that's that. Anyway, the plan for today is to learn about Transformers, really, because I actually don't know really anything. Yeah, so I'm coming at this pretty much. What's this? The word tabula rasa, I guess you could say. Yeah. Okay. Sure. This makes sense to me. This makes sense to me. This makes sense to me. Regularization. I've heard this in the sense of like L2 regularization, which is like you basically just want to make sure that the L2 norm of the weights is like small, where the L2 norm is like the sum of the squares of the weights, I think. But maybe I should get a like more concrete definition of that. So first of all, L2 regularization. Okay. Okay. So it's just reducing the degree of like the solution if we're talking about polynomial fitting, or like reducing the magnitude of the weights by like using the L2 norm if we're talking about L2 regularization and so on. Okay, I suppose this makes sense. Yeah, okay. Yeah, I think the background is reasonable. Oh yeah, this is probably also a good time to pull up Anki because I haven't done the flashcards in a good couple days. Yeah. Okay, so let's see. I'm not gonna do the rooflines ones because they're all like calculations and stuff, and that's not particularly interesting to watch on stream. State the suboptimal coding intuition for KL divergence. So the KL divergence between P and Q is the difference in length of bits the difference in bits of length if you're like encoding. So the true distribution is P, and you're drawing your symbols from this distribution P. But if you believe that the distribution is Q and you create an optimal coding that assumes that the true distribution is Q, then you'll get a encoded like an encoded sequence that is of a length like L, and that length will be like some number of bits longer than the length that it could have been if you assumed that it was the true distribution P, and the difference in those numbers of bits is the KL divergence. What is going on with Anki? Yeah, I don't know why it's so slow. But yes, this is what I said. Okay. Okay, suppose P is the distribution of which word comes next in natural language, and Q is a language model's estimated probability distribution. What's the cross entropy if we're guessing words uniformly? What's the cross entropy if it can predict words with the exact right frequency? Okay, so for the first part, I kind of have this memorized now because I've done this flashcard enough times. It's just a log of the number of words in the vocabulary of the language. So like, yeah. And then for the second part, that's pretty easy to explain. So you have this formula which is that HPQ equals HP plus the KL divergence of P and Q, where P is the true distribution. So if the model can predict words with the exact right frequency, then it means that the learned distribution Q is exactly the same as the actual distribution P, and therefore the KL divergence is 0. So then the cross entropy is just the same as the entropy of the language itself. Yeah. The for the first part, that kind of just comes from like the definition of cross entropy, and also using the fact that if it's got the guessing words uniformly, then the probability is just 1 over the what do you call it? 1 over the like number of words in the vocabulary, since there's an equal chance of any of them being guessed. Yeah. Okay, I'm happy with that. Define DKLPQ. Okay. I think I might have some scrap. Yep, I do. I'll write this down on some scrap paper. And then read it out and compare it. Because, yeah, sorry. Okay, so it's the expectation under P of the information of Q minus the information of P, or the other way of writing this is the expectation under P of log P over Q. Sure, this simplifies to this, because when you combine the logs... Oh, I need to multiply by P because that's what... Oh, wait, no, sorry. They've written the summation and I've given it in terms of an expectation under P. Yes, this would be the same thing, but I'm happy with that. State the Bregman divergence intuition for KL divergence. So I think this is just saying that when you have two distributions and you want to have some kind of notion of distance between them, one way of doing that is the KL divergence. That seems a bit vague. I'm going to have to read the flashcard for this and then probably redo it. Okay, so using entropy to capture how far away it is from 0. Okay, I'll do that again. So, oh yeah, sure. So if we have the true distribution P and an assumed distribution Q, then the Q that minimizes the KL divergence between P and Q is the maximum likelihood estimator. Okay, yeah, Anki's just sort of messing around again. I don't know why, like, whenever I have OBS on, it just kind of does not want to work. Yeah. Expected surprise intuition for KL divergence. Sure, so it comes from the definition that we wrote before, but basically the KL divergence between P and Q is like the difference in expected surprise between if we assume the distribution is a true distribution and if we assume some false distribution, then we would expect to be more surprised than if we assume the true distribution. So the KL divergence would be non-zero for a assumed distribution, which is not the same as the true distribution. Yeah. So cross entropy is, we'll write this down, HPQ equals expectation on P of log Q, which is the same as the sum on X of Px times log Qx. Oh, it needs to be multiplied by -1. Why does that make sense? Yeah, because we want this to be positive, I guess. Yeah, okay. State the Bregman divergence intuition for KL divergence. So, if we want to have some kind of sense of distance between distributions based on like the entropy, then the KL divergence is that, I guess. I actually hate this thing. What is going on? It literally just doesn't work when I have OVSM. I have no idea why that's the case. Yeah. And then the cross entropy is -1 times that expectation under P of log Q. Okay. And that's over. Sure, the weights have to be, you need some to be negative and some to be positive. I think this is called Goulart normalization. Oh, sorry. I seem to remember at least 3 different names for this, but like you basically you want them to be both positive and negative, and then also there's like this thing that you need to do to make sure that the like, so they should be normally distributed, but also they should be like small enough so that you don't get like saturation in like in later layers. Otherwise you just won't be able to learn anything. I forgot what the like name for that is, but I think it's Gloro or Gloro. I'm not sure how you pronounce it. Okay, it's just talking about some of them being negative. What kind of initialization should we typically use? I think this is what I was talking about earlier, Gloro normalization. I think it's also called Xavier initialization or He initialization, and I'm not sure what the difference is between all of those or if they're the same. Okay, I've got at least 2 of those names there. Just answered that. Right. That'll be that for today. Okay, anyway, back to the transformer doc. Okay, so word embeddings. So words have to be represented as a word embedding vector in RD, where D is the like number of dimensions in your embedding space. There's a fixed vocabulary. Each word is a d-dimensional vector. Yep. In the past, you might have learned these separately using these procedures. In more recent research, they are initialized randomly and then learned during training to minimize loss. Okay. For open vocabulary tasks, so where we want to be able to understand words that we didn't see in the training, then we use chunks of words, characters, or Unicode code points. Whether using words or subwords, we need to break text into tokens and then map the tokens to integer indices in the vocabulary. And then the integer indices are fed into the neural network. Hold on. So they're saying instead of using a vector, if we have an open vocabulary task, then we need to... Oh, wait, no. Okay, so they're saying, first of all, we need to break up the text into tokens, then the tokens get mapped to some integer, then the integer gets mapped to a word embedding vector. Okay, so I guess the natural question is, why would you use a vector over just the integer? I don't know, I guess you have more information, maybe you want to like somehow like store the like meaning of the words in the vector, like maybe more similar words could have like vectors that are similar. I guess that makes sense. Sure. So the transformer model originates from that paper, and it was used for machine translation, but it's been used for other things. Yep, it's been caught on in computer vision and RL. So we're going to get a high level overview of what attention is and how transformers use it. Okay, so if we want a more detailed explanation, we can see that, or okay, or this video. We won't be watching a video. Yeah. Attention in RNNs. For transformers, machine translation used was based on current models, which process the input sentence one word at a time using shared weights, generating a new hidden state HT for each position T in the input sentence. What? Okay, so you feed in one word, you get a hidden state, then you pass in the next word and the hidden state from the previous like whatever you were doing before in to get the new hidden state, and so on and so on, and then eventually build up some final hidden state. Okay, and then they're saying the problem with this is that the information from the whole sentence had to be compressed into that one state. Yeah, I guess this makes sense that, like, if we assume there's some like noise in each of the like RNN steps, right? Whatever noise, like, whatever information was stored in the earlier hidden states, the noise in that is going to get like amplified and amplified and amplified. So you'll end up focusing, or like you'll get much better quality on the last parts of the sequence compared to the earlier parts of the sequence, because there's like less noise amplification going on, I guess. I should probably have like Claude open just to ask it and make sure I'm not saying just nonsense. Yeah. Okay, so attention was initially popularized as a solution to this problem. So instead of using the final hidden state to represent the sentence, this guy said we should use all of the hidden states to represent the sentence. That feels kind of like redundant, but okay, I guess. And then at each step of decoding, the hidden states are averaged, weighted by their relevance to the current step of decoding. How they weighted? How they determine those weights, that's something that's learned. In this way, the decoder can just assign more weight, i.e. pay attention, to hidden states that are most relevant to the current decoding step. Right, but like, how does it know which ones to like pay attention to? The weights could be determined most similarly by a dot product. Okay, so this is saying that if we have two hidden states that are like similar, then we should weight those more. So I'm not sure I fully understand that. Hold on. Okay, so you take all these hidden states, and that's your like encoded sentence, and then you're gonna pass all these hidden states into a decoder like thing, and this decoder network will somehow output your translated sentence in a different language. So then, for the how does the decoder work? The hidden states are averaged, weighted by their relevance to the current step of decoding. Okay, so what I don't understand is, how do we know? First of all, what are the steps of decoding, and how do we know like how relevant each hidden state is to that step? So, what are the decoding steps that they're talking about here? Is it just more RNNs? And then the dot product between what? Like, I'm assuming one of them is the hidden states, but then what's the other thing in the dot product? Yeah, this doesn't quite make sense to me. It seems like there's some missing information here. So yeah, I'll ask Claude about this. Okay, so it seems like the decoder is an RNN, similar to this, except where here the RNN at every step takes in an extra token and produces a new hidden state. What the decoder does is takes in hidden states. So like without doing the intention stuff, we would just take in the last hidden state and then produce one token, and also another hidden state, and then that hidden state would go back into the RNN and produce another token and another hidden state. And so, for example, this is probably a good time to like open up Notepad or something. So, I guess the idea is if we have like, what sentence can I translate into French? The cat eats the dog, and we want to translate this. Then it's going to take in the, so we get, this has been translated, and then we have some hidden state h1, and then this, the cat, and we get h2, and so on. And then the decoder will take in the final hidden state, which will be, let's see, h5, because the cat eats the dog, h5, and then the decoder is going to take in h5 and produce le as its first token plus some other hidden state, and we'll call this G1. And then it's going to produce, and then it's going to take G1 and produce le chat, and then it's going to G2, and then it's going to take G2 and produce le chat mange to G3. Le chat mange. Is it le or la? I think it's la, yeah. And so on. And then that won't. I guess it could output some hidden state, but like we won't use this for anything because it's finished decoding. And like I don't know, maybe my French translation is like slightly off. I'm not sure about the gender. I might have like conjugated it wrong, but like this is the basic idea, I think. Okay. And then from there, so that's what it's doing without attention. The idea is with attention we take some weighted sum, or maybe I shouldn't have deleted that. So with attention take some h1 plus h2 plus dot 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 plus h5. And then okay, I guess the problem is, so in that first decoder step, so without attention, what I think is happening is that you just take in the last hidden state and produce a token and a new hidden state. But then, like, because you haven't got a hidden state for that first input, what is that input? Is it going to just be the sum? Is it going to be the final hidden state? Or what? Yeah, I'll ask Lord about this. Okay, so the input with attention is still gonna be the last hidden state. So still at first it'll still be H5, and then produce maybe I've misunderstood the decoder. Okay. Yeah, so this was right. It takes in a hidden state, produces a token plus another hidden state without attention. And then with attention, it's going to take in. So the first stage will just take in the hidden state and produce some output token. But then the next thing, what it will do is context vector 1, I guess we'll call it, and then it'll produce plus another hidden state, And this context one is going to be equal to like the weighted sum of them based on the dot product G1 H N. Sum on N G1 dot Hn multiplied by Hn. Can't see that behind the camera. And then you just repeat this process like recursively until you get your final translated sentence. Okay. Okay, I guess that makes sense. But yeah, there's nothing learnable in this case, I guess. So you're just, like, you're always going to take a dot product of your hidden state to produce the context. So, like, however similar your decoder hidden state at that step is, it tells you how much you want to pay attention to each hidden state. So, yeah. I'm not sure why this works. Oh, wait. First of all, I guess the first thing is, why would we expect the hidden states of the decoder to have any similarity to the hidden states of the encoder? It doesn't seem obvious to me that would ever be the case. Because, I mean, presumably, are you training them separately? Because what I would assume the whole point of having this sort of encoder decoder thing is that you would like train a bunch of encoder models and then train a bunch of decoder models, and then you have like then you can basically like do any language to any other language by just like running the encoder from like whatever language you want to your like encoder language of like vectors, and then you go from your vector to whatever language you want. Okay, this is kind of pointless. Of course, that's why that works. That's the whole point of a dot product. But yeah, why does it make sense that? Yeah. Okay, I'll just have to ask Claude about this. Why would we expect hidden states in the encoder and the decoder to be similar? Because if they're like not correlated at all, then this just doesn't work. Okay, it says that you train the model end to end such that it learns to produce encoder and decoder hidden states that are similar. Okay, so that means that you can't train them separately. Yeah. Okay. That seems kind of bad for translation, but whatever. Yeah. Sure. So that's why that works. And then it's saying the raw scores of the dot product are then normalized by a softmax function. Sure, because you don't want the magnitude of your context vector to just blow up. Okay. So attention calls for NASA way to improve recurrent models for machine translation, but it really took off with that paper. So it gets rid of the RNN structure that we just learned about and uses transformers instead, which takes in a whole sequence in parallel. And in order to capture dependencies between words in a sentence, the authors use self-attention, which is like attention but applied reflexively. What do they mean by this? I'll just hope it becomes obvious later. To compute the relevance of words in a sequence S with respect to each other, rather than with respect to a separate decoded state. Okay. This can be hard to grasp at first. Oh, this should probably like... attention. Oh, I think I'm on French keyboard layout. Yeah. Okay. Helps to think about attention as a function. This function takes a sequence S and a query X, and outputs a weighted average of the elements of S, where the weights for each Si are determined by their relevance to X. So wait, what is the query? So, okay, the query in this, the RNN attention thing, would just be the hidden state of the decoder, but for reasons that I guess I'll make obvious later, we want to generalize to just any like query, not just, yeah, so any query vector, not necessarily just like a decoded state. Okay, so attention as a function. So the query, you have the query, you have the sequence, and then you have attention of, so the query X and the sequence S is this weight, so the attention of S X is, and I'll just write this in words, weighted average of SI, or I guess capital SI, by similarity to query X by dot product. Okay. Okay, so self-attention is just a specific case where instead of using decoded states, the query is one of the words in the sequence. So RNN attention query is a decoded hidden state versus just self-attention query is a word in the sequence. And then to compute self-attention for an entire sequence, we just compute attention of SI for all SI in S. To vectorize this computation, we can compute the weights wij si.sj for all pairs of elements in S with one matrix multiplication. Yes, and then normalize row-wise with a softmax. Yeah. The ijth entry is the attention weight between Si and Sj, which makes sense because the ijth entry would just be at si.sj because of, like, by construction. And then if you softmaxed it, then hold on, which axis are we? Okay, it says row wise. Yeah. Okay. So if we look at this, I guess it makes sense that the diagonal has high magnitude because obviously it's going to be pretty relevant to itself. And then let's look at other places where it's pretty high magnitude. So hello and you seem to have pretty high weights. As this I and love. So I guess linguistically, does this make sense? Sure, because the I love, you need to know that those are like relevant for like conjugation purposes. Like if it was hello, he loves you, then you would obviously translate that differently. And then hello and you, I don't know why, but sure. And then why is this matrix not symmetric? That seems weird. Because yeah, I mean it's pretty much almost entirely symmetric. The only difference is this here, which is quite weird, right? Because you would expect it to be like symmetric, as far as I can tell. I don't see why it wouldn't be. I guess this is something to ask. Anyway. So, anyway, using attention, self-attention, as we described, you get that. And then these weights are used to transform the input sequence to another sequence where each element in the output sequence is the weighted average of the elements of S based on their relevance to Si. So you essentially, you can add on some like other tokens to your current token to like based on the relevance. So if like, so for instance in the case of hello, right, so since we know the rows have to add up to 1, right, that's the axis along which you're sort of adding up the token vectors. So originally you started with hello, but now you're going to get mostly hello, and then a bit of I, and then a little bit of love in you. Whereas for I, you're still going to get mostly I, but then you're also going to get a fairly high amount of love in you, and a little bit of hello too, and so on, right? And I guess this is relevant because, like, for instance, say when you're decoding love, right, you want to know that it's I love and not they love, because in English, I love and they love, like, the love is the same, but maybe in another language it would not be. Yeah. So, vectorize, this looks like multiplying the matrices W attention and S, so that each output element Zi is equal to a weighted average of SI's weighted by the relevant row of W attention. Yep, that makes sense because you're just doing this, and then you'll have S as your, like, column vector here. Or not column vector, but your column matrix. Like, you have a bunch of matrices, each of the columns of which are from your S. Yeah. Okay. And then the meaning absorbs some information from its neighbors, but yeah, okay, which is basically what we were talking about earlier. So queries, keys, and values. So one thing that might be missing is the opportunity for learning. As set out above, it's deterministic in S, and there's nothing trainable. Yep. The gradients can propagate back to the original word embeddings, but the layers, the attention is not parameterized, so it can't learn anything to solve the specific task. Okay. So yeah, the only way for it, so it would essentially have to learn the embeddings such that the things that it wants to be similar are similar. If indeed it is learning the embeddings at all. If it's like using a pre-chosen like embedding, then you're basically just screwed. But like, yeah. So without whatever it's going to introduce next, you would just need to hope that the like the gradients could like propagate far enough such that it like learns embedding vectors which are like similar when we want them to be similar. Okay. So in attention is all you need, they introduce queries, keys, and values, and then that puts trainable parameters into attention layer, and that allows it to adapt as the neural network trains. So in the self-attention that they just described, SI is both the query, the key. So the query is the X in the like, so it's the thing that one of the elements that we're comparing the similarity to, and the key is the other thing that we're doing the dot product with, and then the value is what? So the query that all elements in the sequence are compared to assess their similarity, to compute the attention weights, sure. It also acts as the key, as an element of S when its similarity is compared to the query X, to compute the attention weight between itself and X, sure. So that's the SI.SJ or S transpose. And then it acts as the value for averaging. So the sum on I of the ith weights times the, okay, so, oh, I see. So you can want to learn the queries, you'd also want to learn the key, and then you'd also want to learn the value. So instead of just using words that are embeddings of words that are in the sequence as your values for that are going to make up your context vector, you can instead just like learn some other vector that you're going to use instead. So, and then the way we do this instead, we're just going to have three learnable matrices, WQ, WK, WV, and then we're going to then get some vectors out of those by multiplying with the sequence. So we're going to, QI will just be some weighted average of SI. KI will also be some weighted average of SIs, and the same for VI. Sure. And then the attention matrix would just be the softmax of Q K transpose over square root D subscript. What's D subscript K? The square root of the dimension of queries, keys, and values. What? When it says that, okay, the dimension of queries, keys, and values, it means just whatever length of the vector Q, K, and V. So, yeah. And that's to avoid vanishing gradient problems. Okay. And then this attention of S on S, which is just self-attention, is the attention times the value. So, hold on. So why are they called queries, keys, and values? What? So why does that make sense? So you generate the queries, keys, values in like some way, which is just you multiply. So you do S times some learnable matrix. That's fine. This, I guess, is the one that I mostly don't understand. So the attention, you're doing the sort of query times key. So key transpose. So what does that sort of represent? Query key transpose. So that's like the similarity with something. I don't know why they're called keys and values. It seems like that it's supposed to be mnemonic in some way, but then I don't understand like the intuition behind it. And then is there an obvious reason why value one is called value? I don't know. Okay, so it's supposed to be like a key value store. So you have a query, and then you're looking up the key that most matches with the query, and then you're getting the value associated with that. But then, instead of a lookup, it's sort of like you're summing them. Okay, so by doing QK transpose over square root DK, you're saying, okay, which keys are most similar to my queries? And then by doing this thing, this is like your lookup. The self-attention is like your lookup. And then we're just summing them so that the keys that are most similar to your query, like, contribute more to the self-attention than the keys that are less similar. Or the values correspond to the keys which are less similar. Okay, so I guess that makes sense. So, queries, keys, and vectors. So, I can't screenshot this, is no good. So Q equals SWQ, and the same for K and V. Okay, then QK transpose divided by square root D sub K, dk equals dim and values. So this is like, so that one's fairly self-explanatory, and then this one's like, look up which keys are most similar to my query. And then the next one, which is, so self-attention equals W attention B. So this is basically saying, okay, so we have, like, we know which keys are most similar to my queries. Now for the ones that are most similar, we want them to contribute most. So look up the values corresponding to those keys that are most similar and make them contribute more to the output. Which are most similar to the weight, sorry, the which so make the values which correspond to the weights, to the keys which are more similar to the query contribute more to my output. Okay. The whole process is summarized below, mostly zoomed in on the self-attention computation for the first element. So you start with Z, you get your Q's, K's, and V's by multiplying with your matrices. Then you're going to find all the respective dot products to get some weights. Then you're going to use those weights to like find out like how much of each of the values are going to contribute. You sum that up and then you get some output vector. Cool. So with only one set of learned weights for projecting all tokens into queries, keys, and values, yeah, then that might be a problem. It's also difficult for a query to attend to multiple positions at the same time, since with softmax the largest value dominates. What? I mean, surely couldn't it just like say assign like, so let's say we had, I'll go back to here. So like let's say instead of 0.8 and then 0.1 and 0.05, 0.05, why couldn't it do like 0.4, 0.4, and then 0.1, 0.1, right? And then like weight the most on hello and love and not I and you. I guess there's nothing stopping that. But then, yeah. And what they're saying. They're saying it's difficult because the largest value dominates. Yeah, that makes sense, because if you're thinking about like the largest that the model is going to output, right? If there's one that's even a little bit bigger, because you're doing the exponential, right, that's going to contribute much more. So the model will have to learn to output stuff that's like pretty much exactly the same, which is like unlikely, or it's going to struggle to do that. Okay. To introduce even more flexibility and allow more representational subspaces in this, I don't know what they mean by that term. Well, I kind of have an idea, but I'm not exactly sure what they mean by it. But they say, okay, what if we just repeated it a bunch of times with different WQ, WK, WV? And then in practice, we can just do this in parallel, sure. And then each set of W, Q, K, and V are the attention head. So this is like a machine which does attention, I guess you could say. And then we get a bunch of, and then based on that, we're going to get multiple different output vectors instead of just a single one. So a self-attention layer with H heads produces a stack of H different outputs, sure. Since each set of weights is different, each output in the stack is different. Yeah, but then how are we going to use all those different attention vectors now that we have multiple? Okay, so you just concatenate it and project back to the... Okay, I get how concatenation literally just means like, right, put one after the other. But then how are you going to project them back to the embedding dimension? What does that mean? Hold on. Okay, by project they just mean multiply by some matrix such that your output is going to go back to like being the dimension of your embedding vectors. But then this projection, are we learning it? Okay, so we learn the projection matrix as well. So typically you're going to want to have dk smaller than d, and often dk is equal to dk times h. So then that means once you concatenate them, you're just gonna have, then your what do you call it? Your projection matrix will be square. Okay, and then that's good because it means, because if it was like wide, then it means you're just like introducing redundant sort of sorry, if it was narrow, so like if it was had fewer columns than it had rows, then you're going to be sort of introducing. Hold on, let me make sure I'm getting this right. So, why do we want projection to be square? So case 1 is when tall / narrow, so that means columns less than rows, and then case 2 is just when wide, so then there are more columns, yeah, and then that's greater than rows. Okay, so when there's fewer columns than there are rows, then what's going to happen? Well, we're going to get something that has like, it's going to be wider than it was originally, but the rank is going to be the same. So there's going to be some like, we're going to be introducing like redundant information. Because and then in the other case, so if there are more columns than rows, then some of the, then what's going on? I guess we're gonna have to like sort of crush some of the, so we're gonna have to lose information by collapsing. Dimensions. Okay, and I'll ask Claude about this to make sure that I am getting this right. Oh, I should have changed that to case 2, but whatever. Okay. So it says the second case makes sense. The first case, wasting capacity. So the representation is in a lower dimensional space than. Okay. Sure. So it's like if the some of the if the concatenated length of the vectors is like lower than the embedding length, then necessarily you're gonna have to how do I say this? Yeah, there are just less dimensions, and then when you do the projection, the not the rank, but they're not all gonna be independent of each other. So you're in some sense just there's no point doing that because you're embedding vectors, even though they're the dimension of your embedding vectors, they're not going to contain as much information as they could if you were to use if you were to make it such that the sum of the length of the concatenated attention vectors is the same as the length of the embedding vector. Okay. But I think that mostly makes sense now. So sort of. So that's why we need it to be square. So that's why we need d equals dk times h. Okay, so that's multi-head attention. The transformer encoder. So hold on, what am I even looking at here? So you start with the inputs, you embed them, you do positional encoding, I don't know what that is. We do multi-head attention, which is what we were talking about. Then add and norm, so I'm going to add in some amount of the original positional encoded input embedding, and then we're going to take the batch norm, which just means so for every feature hold on, oh crap, I can't remember which way around this is, but it's either you add up, you take the yeah, no, I can't remember if this is, because it's either you're normalizing with respect to the mean and variance of all your activations for a given batch sample, or it's with respect to all the different values of that same activation across different batches, but I can't remember which one it is. And I know I asked about this, so I'll have a look in my previous chats. Okay, so it seems like it's, yeah, so you normalize across the batch. So that means so if you have a bunch of, how do I put this? So the output of the same neuron, you could think of it as, or the same node, but for different batches, you're going to look across all of those different neuron activation. So that same neuron, look at what its activation is for all the different samples in your batch. Then you're gonna find the mean of those, find the variance of those, and then what you're gonna do is for each of them you'll subtract the mean of the batch and divide by the square root of the variance to get some normalized value, and then you also add in some of the initial like positional encoded thing, and then you'll pass that through an MLP, and then do the same thing again, and then this goes into. Wait, what does it mean by outputs? What? How? Okay, I'm not quite sure what's going on there because this part maybe kind of makes sense, although I don't know what a positional encoding is. The problem is here, how are you supposed to take in the outputs as an input? What does that mean? What? Because usually it'll be like inputs, outputs, but instead you've taken inputs and outputs somehow, and then you get output probabilities, whatever that means. Yeah. So, unlike RNNs, transformers digest the sequence all at once because of what we talked about when they take in that matrix S. Yeah. And then, unlike CNNs, there's no notion of local relationships because it's going to compute the self-attention of all input vectors with respect to all other input vectors for the entire sequence. And then it's going to summarize that. And then it's permutation invariant. Yes, that makes sense, because if you were to swap two of the columns in S, then that's just going to swap, like, two of the columns in, like, your final thing. Right. But then this is bad, because we want it to actually change with permutation. Yeah, okay, that makes sense. And then we have to add information to do this, for it to change meaning when we change the position. And the way they do this is periodic functions of various wavelengths. So they compute a series of sine and cosine vectors functions to get position vectors p1, p2, pn. What? Yeah, I don't quite get this. I'll have a look at. Oh my god, what? Okay. So yeah, it seems like before this is kind of information that was already the original document. So the first idea that you'd get is to just assume, add like some number where 0 represents the first thing and 1 represents the last thing, and then I guess there'll be like equally spaced between that. And then the problems would be that you can't figure out how many words are in a specific range. Okay, that makes sense, because the longer the sentence is, the shorter the delta is, and so it can't like learn exactly how many words are between like two of these. Another idea is to assign a number to each time step. Manually. Okay. And then the problem with this is that it could get sentences longer than the ones in training, and then also the values could get fairly large, and then it might not see a sample with a specific length, and that would hurt generalization. Okay, and then the criteria that we want are that the encoding should be unique for each time step. The distance between two time steps should be consistent across sentences with different lengths, and then it should generalize to longer sentence and have bounded values, and it needs to be deterministic. Okay, and then what they do is introduce a vector. So let T be the desired position in an input sentence, PT in RD. So the PT is, I guess, the positional encoding of T. Yeah, and then let D be the encoding dimension, so where D is some multiple of 2. Then F is a function from the natural numbers to a d-dimensional real vector, and F produces PT, and it's defined as follows. The positional encoding of T, the ith positional encoding of T, so the ith element of the positional encoding of T is equal to the ith element of F of T, which is defined as sine of omega subscript k dotted with or multiplied by T if I is equal to 2k, and cosine of omega k times T if I is equal to 2k plus 1. So it's saying if I is even yeah, sorry, what is k? So an omega k gives 1 over 10,000 to the 2k over d. What's k though? Oh wait, no. Okay, so this is kind of confusing. So it's basically saying that k needs to be an integer, I guess, and then in the case where I is even, then you just do this thing, and in the case where I is odd, then you do this thing. Okay. Okay, so that's kind of what we described, where you just have sine and cosine omega 1, and then, yeah. So as it can be derived from the function definition, the frequencies are decreasing along the vector dimension, because, yeah, as the k gets bigger, omega k gets smaller, so therefore the frequency gets smaller. Yeah. And then that's why d has to be divisible by 2, because we're going to have sine and cosine, so that there's going to be like an even number. Okay, and then, so how does this represent a position? So, suppose we wanted to represent a number in binary format, we would do it in this manner. So the LSB alternates on every number, then every 2, every 4, and so on. Okay, but using binary values would be a waste of space in the world of floats, sure. So we can instead use the float continuous counterparts, which are sinusoidal functions, Okay. And then by decreasing their frequencies, we can go from red bits to orange ones. I'm not quite sure what they mean by this. So they mean they like decreasing the frequency is like in some sense analogous to going to a more significant bit. So that means here the first elements are somehow more significant, and the last elements are somehow less significant. So the LSB bit alternates on, yeah. So wait, how much does the frequency change by when we increase k by 1? So, okay, it's not like it doubles or anything. It just changes based on this. Sure. Okay, this doesn't really feel like an explanation. Okay, but sure. Let's just assume that we have this d, and somehow it's like relevant to t in such a way that like the model can learn it, and it has the properties that we want. Then it says, earlier in the post he mentioned that positional embeddings can be used to equip words with positional information. How do we do that? Okay, we literally just add the positional encoding to the embeddings, and then in order to do that we need to make the positional embedding dimension equal to the word embedding dimension. It feels like adding shouldn't work. I don't know, because you're just like losing information there, right? I guess one benefit of doing it this way is that like hold on. But don't you still? I guess it's fine because like the number of t's that you can represent is like high, but it's like is it not still bounded? Because at some point you're gonna get like t large enough that like that the representation is gonna be the same, because sine and cosine are periodic, right? So I guess the way that you compound that is by this constant, right? You want to choose, so here is 10,000, but like if you chose some bigger length or some bigger number here, then the period of this would be like longer, and so you'd need much bigger t in order to get pt to repeat. Okay, and then it says for any fixed offset k, p of position plus k is a linear function of p pos. And then the proof. So for every sine cosine pair corresponding to frequency omega k, there exists a linear transformation M that's 2x2 real matrix, such that this holds M times sine cosine equals sine. Yep. Okay, this is. I don't know. This just kind of is obvious, right? Because you can just like you have this sine like addition formula, right? Like Um, yeah. Yeah. Okay. That makes sense. And then we can find M for other sine cosine pairs. So therefore, PT plus phi is a linear function of PT. Okay. I'm happy to accept that. Another property of sinusoidal position encoding is that the distance between neighboring time steps are symmetrical and decays nicely with time. So what do they mean by symmetrical? Oh, so they mean the distance of the vectors themselves. So the Euclidean distance of the vectors between neighboring time steps are symmetrical. So what does this mean? The distance between 14 20, isn't that sort of, hold on, what do they mean by distance between neighboring time steps here? Okay, so the dot product of any okay, this is a graph of the dot product, and it's obviously going to be symmetrical, right? Because if you're just taking the dot product is inherently symmetrical anyway, right? Like A dot B is the same as B dot A. But it's one thing that's good is it's symmetrical along the other axis too, right? So, like, for instance, the dot product of 0 and 0 is the same as the dot product of like 20 and 20, but there's no reason for that to be the case a priori, but it just happens from this choice of encoding. Okay, and then why are they added, which is what we asked earlier. Okay, basically there is no reason why it doesn't have disadvantages. Okay. And then it's saying because it's learned and because the first few are like more significant, basically what it does is like it will learn to like not put stuff in the first few elements in order to like not interfere with the positional encoding, and then learn to put stuff in the lower ones where the positional encoding is not as relevant because it's like 1 or 2 words difference. Sure. Doesn't the position information get vanished once it reaches the upper layers? And then it says, okay, it has residual connections, so that's talking about this here. So when we do the add back in, that's the residual connection, and here, and so on. And then the residual connections allow the information about the position to propagate further. Yes. Why both sine and cosine? I mean, you could choose. It's basically going back to that proof, right? Like, as long as they have this property, then you can use it. But I'm trying to think, are there any other functions that I'm aware of that this is the case? I don't think so. Well, not that I can think of immediately. I guess I'll ask Claude about this, because I was thinking maybe hyperbolic sine and hyperbolic cosine, but those aren't periodic. And then what else? We could have like 2 square waves that are like offset by a certain amount, but I don't think that would work. Are there any non-trivial which because the only thing I can think of is like sine and cosine or like the constant. But obviously, if these are just constants, then this is like useless. Yeah, we'll see if Claude can find something. Okay. It seems like the only case where they're like bounded and periodic is sine and cosine. Because the other solutions that Claude found are exponentials multiplied by sinusoids, which are obviously not bounded, or not necessarily bounded, depending on like what domain you're looking at. Exponentials, 1 and t, or yeah, basically sine and cosine are the only ones that can be used that have like the properties that you want. Okay. So and then layer normalization. Okay. Batch norm is normalizing the same neuron across a batch of inputs. Yes, that's what we talked about. And then layer norm is sort of the other thing, so you're normalizing against the other axis, which is just like all your activations for a single batch sample, but for different neurons. Okay. And then it's saying layer norm is better in some sense because it's agnostic to batch size and can be used in recurrent architectures. In the transformer, it's only used to average across the embedding dimension. So we normalize S1 through Sn separately. So we're doing layer norm to normalize S1 through Sn. And then after that, we take a linear layer, so multiply each neuron by a learned weight W and add the bias B. Okay, yeah. Wait. So they're saying we do the self-attention thing to get some more vectors, and then we layer norm each of those vectors, and then pass them through some like weight and bias. Okay. And then more recently, you can omit the bias, or even like get rid of the centering, so not even compute the mean. And then dropout is dropout, but I'm familiar enough with that to like not really read that properly. Position-wide feed forward. Okay, so the same. So we train some small neural network that we're going to apply to each sequence element after this self-attention has happened. Okay. So we do the multi-head attention, then we do the feed forward, and we're going to have some like residual stuff in the layer norm as well. And then we also use dropout in this feed forward, so as to not like what's the word, like overfit. And then sometimes they even use dropout in the self-attention. And then also sometimes they do pre-norm, which is layer norm before, what's the sub-layer? Oh, so as in they do the layer norm before the feed-forward network. Yeah, okay, so they're talking about doing layer norm, then feed-forward, then add. Okay. And then apparently this like makes it easy to train. Transformer encoder is one half the transformer model. And then, okay, the transformer decoder. I think this is probably, how long have we been streaming for? This is maybe a reasonable stopping point. Or at least definitely a pause point. Because I have something that I would like to do quickly. But yeah, let me look at the stream length and stuff. I think I mostly understood this. Although, we will have to come back and implement for sure. I feel like I definitely understand sort of the reasoning behind it. It seems like at every step they're doing things that broadly it makes sense why you would do this. Like, it seems justified, even if I would not have come up with it. Okay, so it's been not yet 2 hours, like an hour 40. I'll probably give it a bit of a pause. I'll turn off my camera and mic, and be back in a little bit. And probably just read the decoder part because it seems a bit shorter, and also like it'll be nice to have finished this document by the end of the stream. Yeah, see you in about 5 to 10 minutes or so. Oh shit, wait, someone literally joined the second I'm about to go for a break. Hi. I'm about to go for a break, but we'll be back in 5 to 10 minutes and finish reading first. Yeah, maybe not the best timing. I'm sorry, and 03K. Yeah, I probably mispronounced that name, but yeah, I'll be back in a minute. I just need to go do some stuff. Yeah. Alright. Yeah, we're back. Let me reopen the camera. Yep. Okay, I'll check the chat quickly and get back to it. There seems to be nothing new. Okay, yeah, so the transformer decoder. So the goal of the transformer is sequence the sequence, but all we have done is encoded the sequence. To get a legible output sequence, we need to decode. Okay. So during inference, we don't have a target system sentence, and generate the output one word at a time. So at each decoding step, we receive the encoding of the input sequence and the output sequence generated so far. Yeah, that makes sense. So that's what it means by autoregressive. And then the decoder outputs a probability distribution over the next word, and we either sample it from it or greedily choose the best next word, and then add that to the output sequence and repeat. Okay, so for translation tasks, we have the input in our input language, so Spanish, and then we go through the encoder, and then we get some embedding. Then the decoder will start with some. Okay, so here it's got we already start with start of sequence I have A, then the embedding from the encoder, and then we're going to decode to get something. Okay, so in training, we're forcing it to have some output sequence, and then we're just saying, okay, output the next word, probability distribution, and try and match it to the actual probability distribution. And then in actual use, we're just gonna auto-regressively do this. So we'll start with start of sequence, and then we'll hope that it produces I, and then have, and then A, and then car. Okay. So doing this naively, training takes as many decoding steps as deployment. Meanwhile, the decoder architecture is producing output that's mostly discarded. Sorry, what? I've kind of lost it with this paragraph, so. Oh, with these two paragraphs. Okay, this makes sense. I suppose the correct translation is I love you a lot. Okay, sure. This makes sense. So at each step, we'll compare what the thing outputs to what we wanted it to output, and then obviously use that to update the weights. And we won't continue with incorrect things. We will literally just try every prefix possible to find the next word. Okay, and if we do this naively, Then training takes as many decoding steps as deployment, which makes sense because you have to do one decoding step per like word in your output sequence. Giving it more, yep. Meanwhile, the decoder architecture is producing output that's mostly discarded. Sure, because most of the time the output is going to be not the same as the what you want it to do, and so we're just discarding it. Okay, and then, but apparently there's this thing called masked self-attention, which allows us to feed the entire target sequence to the decoder in training. Use a mask on the attention matrix to stop it from looking ahead. Oh, okay, so it's like when you have that attention weight matrix, you can make the top half 0, and that means the model can only pay attention to the words at or before that index. Are they going to show the matrix at any point? Yes. Okay, I was correct. Cool. Do I need to read this whole thing then? Sure, I will, because maybe there's some detail that I'm missing. But that seems to be the general idea. So receives the target sequence and the encoded input sequence. We want the output to correspond to okay, and then we should do that before the softmax. I guess that's the other key point that I did not mention. Wait. Okay, hold on. So they don't have to add up to... Okay, no. So after zeroing out, then the softmax normalizes them. Okay. So this would be 1, and this would be like some value such that these both add up to 1. And this will be like 6 out of 7, and this will be 1 out of 7, and so on. Well, no, it won't be that, but like, this will be bigger than 6 over 7, and this will be less than 1 over 7. But you get the idea. Because yeah, it's softmax. Blah 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 blah. The one thing is, I feel like this will make sense if we're doing translation, and how do we use this to do generation? Because in generation you don't have there's nothing to encode, right? You're just starting off with like. Actually no, I guess you start off with the prompt, so you can encode the prompt and then like use that to, I don't know. I'll just read it and see what it says, and then we'll see if it makes sense. Okay, so we've talked about how it processes the target sequence during training, or the generated sequence so far during deployment. But we need to also digest information out of the input sequence, and we do it using attention, like OG, RNN attention. So we'll take in the output of the previous decoder layer and the final encoder output. So the queries are from the decoder sequence, and then the keys and values are from the encoder. Okay, I'm gonna have to reread that. That doesn't fully make sense to me. Well, the queries come from the decoder sequence, so that's the decoder hidden states get multiplied by some matrix to produce a query matrix. And then the keys and values come from the encoded, so that's what the input sequence. So for each decoder token T1 through Tm, we're gonna use its queries to compute the attention weights relative to each encoded oh, okay, so this is just like, okay, so this is, yeah, it's like the RNN attention that they were talking about before. So we compute the similarity between the decoder hidden state and all of the encoder states. Or no, the final, but we're just using the final encoder and output. And we're going to compute the similarity. So that makes sense. And then we're going to use the values based on encoded output. Okay. Sure. So information flows from the encoding of the input sequence into the decoder. That makes sense, because the decoder is basically, in some sense, the hidden states of the decoder are like looking up information from the encoded sequence and like using that to inform the future decoding steps. And then we don't have to worry about masking because the decoder is supposed to know about the entire input sequence. And the decoded states shouldn't interact with each other, except obviously through like the decoder hidden states are used like to produce the output, and then it's auto-recursive. Okay. So putting it all together, the decoder block and transformer decoder. So you've got your output sequence. Okay, so the output sequence is the like what the translation sentence should be. So this is like a training example. Then you've got your output embeddings, so that's something that you would learn how to do or just like have pre-done. Okay, and then we're gonna do mask multi-head self-attention. So this is to do the like find out probabilities for like each possible prefix of the sequence. And then we're gonna do some feedback and layer norming. And then multi-head self-attention on that. So this is from here, this is like, so below, you can't see me pointing at the screen, but I guess you can see my cursor. Below where my cursor is, that's the encoder, and then after that is the decoder. Sure. But no, hold on, what? So this is decoder, and this is also decoder. Hold on, I think I must be misunderstanding what the mask multi-head self-attention does, because my thought was that's just to like, you get because my thought was that's just for training. I didn't. Why would you need to use this in inference? Okay. Okay, so wait. Also, it's not actually 0. It will be set to minus infinity. Uh, okay. Yeah, because my understanding was you're just doing this to like not have to do a bunch of steps when you're training. But then why would you keep this after that? Okay, so you do the mass multi-head self-attention. You're gonna get... What do you get out of this? And then why do you have to do multi-head self-attention after this? That doesn't really make sense to me. Okay, we'll leave that first bit for now, and then from there we've got multi-head self-attention and also the encoder output as an input. That makes sense because you're just doing what they described, where you have your decoder stage hidden layer as the query, and then your keys and values are from the encoder output. And then this allows you to somehow like learn things about, or not learn things, like query stuff from the encoder output. So it could be like asking, okay, is there a first person pronoun in the position Y or something? Okay. And then you're going to do some feedback, and then after that you do a feed forward network to just like, I don't know, it's for reasons. And then you're gonna softmax that to get your output probabilities. Sure. So yeah, this thing that doesn't make sense to me is, what is the multi-head self-attention doing outside of training? Why would you include that there? And I don't think the documents super answer that for me, so I'm gonna ask Claude at this point in time. It's probably best to take a screenshot of this rather than try and type it out. Okay, so it seems like the masking, I guess the way of thinking about it is it is basically saying that the output needs to be causal. So later position tokens can only depend on previous position tokens, and so the output that we get from this should reflect that. And if we do the masking, it does reflect that. And then from there, we can just do the rest of the stuff. So, we have something now to query the encoder with, and do attention on that, and then if do some feedback, and then pass this through just a normal MLP to get some probabilities. I guess that makes sense at a higher level, although it seems fairly arbitrary. I don't know. And also, I still don't really get how you would use this to do ChatGPT type stuff where you're not doing translation. Okay, so if you want to do stuff like understanding, classification, summarization, you want to only use the encoder part, and then for GPTs, you want to only use the decoder part. So you're just fed a bunch of text, and you'll task it to predict the next unseen token. I guess the one question would be then, if we're doing GPT, then what happens here? Instead of encoder output, what are we querying? Here it's labeled output sequence, but it'll be the input sequence. I guess. I don't know. Okay, I guess that's something to ask. Okay, so for GPT, you just drop this middle block entirely, apparently. You do mask multi-health self-attention, and then you do a feed forward, and that's it. Okay. Yeah, definitely gonna have to review this, but I think I've made enough progress to like stop for now. Uh, yeah, I think this was useful at a high level, although I'd still be pretty lost as to like actually implementing this. So yeah, that's for tomorrow, I suppose, because I should be able to stream. Anyway, yeah, that's it. I'll end the stream there. Bye, and hopefully see you tomorrow.